Hello, my name is Omalbe, and this is Lab 1 Constant Velocity Motion. In this lab, we will be dealing with constant velocity. According to Newton's first law, an object in motion stays in motion unless some sort of force is applied to it. Therefore, if the net force on an object is zero, we should see its motion show a constant velocity. And this is the observed motion that we are going to be looking at. To model these motions, we are going to be using three formulas. The first one is the velocity update formula, and this formula is used to figure out velocity when an object experiences some level of acceleration. However, since the net force is zero in this case, we should not experience any acceleration, so the initial velocity should equal the final velocity. The second formula we're going to be using is the position update formula. This updates the position based on velocity times change in time. In this formula, we should experience some change because even though there is no acceleration, there is still constant velocity. So the position should constantly be updated from initial to final. Finally, the last formula we're going to be using is F equals ma, or force equals mass times acceleration, which can also be rewritten as acceleration equals force over mass. However, since in this scenario the net force is supposed to be zero, acceleration is gonna be zero over mass or zero, and so there should be no acceleration, which connects back to there being no change in velocity and there being constant velocity. To conduct this experiment, I used a bottle and I rolled it down a flat table. Although it doesn't look flat in this image, it was flat. The image is just slightly tilted. And here is the data that we observed from this rolling video using the tracker application. Now we had a lot of data points, so which is why it is depicted in a chart and not in table format. As you can see, it is mostly linear and to the point where the linear line of fit is basically hidden behind the data points. This data has a slope of about 996 and it has a y-intercept of about 20, which means that the objects are about approximately 20 units at the start of the video, and for each second, it it traveled about 996 units. Using the data that I had observed, I created the following computation model. Now, although there's a lot of coding, there are two main pieces that need to be looked at. The first at top shows the initial position and the initial velocity of the ball. Now, this connects back to the slope and the y-intercept that I found in the previous slide. You can also see that delta t is 0.02, as this was the steps between each recorded point. The second important piece of code can be seen in the second snippet shown. In this snippet, it shows how the ball's velocity is updated with the vector of 0, which means it is not updated since the force vector, which is displayed, is also 0. However, the position of the ball is updated using the formula ball position plus ball velocity times delta t. This should mirror the equation seen in the first introduction slide, and this allows us to calculate and predict the ball's position for every change in delta time. Here you can see the predicted data and the graphs created based on that. As you can see, just like the observed data, it is a very linear graph. Now, comparing the observed and the predicted motion, you can see that they practically line up on each other. Although there are some variation, especially with the observed being lower at the starts and the end of the graphs, most of it lines up pretty well. This is because the observed motion matches the predicted data fairly well. Now, what do the results mean for our conclusions? They mean that the observed motion followed the prediction models. Hence, the objects followed Newton's laws of motion, which were used to create the equations seen in the first introduction slide, and the graphs, the prediction models, were followed by the objects. Therefore, Newton's laws of motions can be observed in real life. Some possible errors for this lapse were the bottle used was not exactly smooth, therefore, there were bottle dents, and this meant that there was a non negligible level of friction which could have skewed the data. There was also manual tracking error as the tracker application used um, made me manually input every plot of data. Now, what are some hypotheticals with this experiment? What if instead of the table being flat, the table was tilted? This would introduce an actual force of an additional force, being the force of gravity, which would attract the bottle to roll downwards towards the bottom of the slope. This would mean that the acceleration would not be zero as the net force isn't zero, which means we would not see constant velocity. On the other hand, if the object rolled was cylindrical, we would see other forces play in hand, which would also lead to the velocity not being constant. That's my lab. Thank you.